So welcome to all once again in this ATAL Faculty Development Program on Advances in Solar Photovoltaics and its design for e-vehicle. Today we have an eminent speaker, Dr. Sujit Kumar. Okay. So Dr. Sujit Kumar is a well-experienced academician. He did his PhD from our university only, from our Mahana Pratap University of Agriculture and Technology only, and he has published many research papers in different international and national journals. And one important thing is that he has published 7 patents. Okay, 7 Indian patents under his name, and he is also reviewer of many journals like eminent international journal. Then he has organized many FDPs and seminars, and an ample year of approximately 10 years of teaching and research experience. So today he is with us to share his knowledge with our participants. So I welcome Dr. Sujit Kumar. Yes, Dr. Sujit Kumar, are you there, sir?
Yes, sir. Am I audible?
Yeah, you are audible. Okay, so I'm just stopping my this screen sharing, and I welcome all the participant, all the dignitaries participant on this second day of our ATAL program on advances in solar photovoltaic and design for e-vehicles. Also, I like to mention that all our lectures are being live telecasted on YouTube. So uh, you can go through the YouTube under the channel Gyan_Hub. Okay, if you do not understand anything in between the lectures, but if you have any queries, then we have a session from 9 to 9:30. Okay, there you can ask the question. Okay, so now I hand over the mic to Dr. Sujit Kumar. Dr. Sujit Kumar, please start your session.
Hope my screen is visible to everyone, right?
Yeah, it is visible, Dr. Sujit.
Okay. So thank you so much for the introduction, sir, and good evening all the participants who have taken part in this ATAL FDP. Today's topic of my discussion will be the advances in batteries used for the solar photovoltaics. So basically, as we all know that particular solar photovoltaics, if we want to use for the conventional uses, where the applications based on the DC or as well as for the AC applications, we required some batteries for the DC applications. So what all the batteries available, what all the advancements, the paradigm shift from the conventional batteries to the advanced batteries used in the solar photovoltaics. So based on that, I will be giving the contents. The first, well, these are my topics, what we are going to discuss. The first, I will be discussing about the general description, about what all the batteries are there, what are the traditional conventional ones, what we are using till now. And then we'll compare from what all the traditional battery systems when compared to the advanced PV batteries. Then we are going to discuss about the advances in the discrete PV battery designs. Then we are going to see how the advancement has took over place in the integrated PV battery designs. In the integrated PV battery designs, I'm going to discuss about three designs, that is direct integrations, photo assisted integrations, and the redox flow battery integration. So basically, when discussing about the general description, as you can see here, so this topic which we are going to discuss about what are the things I'm going to tell, that is the advanced concepts in the PV battery system, designing while providing the critical discussions and reviews and the prospects based on behind the uh, conventional PV battery systems. So in designing these PV batteries, we have the technical challenges, like the most common technical challenges are the energy density, efficiency, stability. So when comes to this part, I will tell you about how this energy densities, efficiency and stability can be improved when we are going for the integrated in the advancements. Okay. So this presenting this particular perspective on the opportunities and the future directions. So I will be giving the key strategies on developing such PV battery systems. So key focus should be on the development of innovative designs that must be incorporating the high capacity, because this is exactly the what the researchers are being into this development field. So they are looking for the high capacity, efficient and the stable materials. So what materials and the efficiency of the PV batteries are the major concern ones, and the stable materials, what all the materials which will be going to be demonstrated, or what all the materials which is going to be available in the integrated PV battery systems. So as we know that energy for the sustainable future motivates today's R&D, enabling the technology such as smart consumers, electronics, electric vehicles, and the smart grids. So since these technologies demand the use of batteries like sunlight, we know that whatever the abundant source which we are getting from the sunlight can be elevated in the form of batteries, while batteries can address the photovoltaic intermittencies. Looking for next, as now I will be comparing the traditional ones versus the advanced battery systems. So what happens here, you can see here in my figure, that is combining what energy, that means the combining the energy generation and the energy storage in one single unit, that is called the integrated design. Okay, so combining the energy generation means from the sunlight, what exactly the PV panels we are going to generate, and the energy storage, batteries, will be combined in a one single unit. Previously, it was like separate unit is there. Since you know that since till now we are separately is showing the block diagram also, like PV panel is there. Then we are using the batteries with the help of DC chargers or the DC charge controllers, and then we are giving to the load. Okay, but now in the integrated systems, which is now the advanced systems, we are going to club these two units, that is the PV panels with the energy storage battery systems. Okay, so this integrated design of PV and the battery will serve as an energy sufficient source that solves the energy storage concern for the solar cells and the energy density of the concern of the batteries. Okay, so you can see here in the figure A, this is the conventional one which shows that PV's panels are different. Then it is connected with the batteries, and then we are going to connect with the load. While when it comes to the integrated, this B to D, B figure, C and D figure will be the term as the integrated PV battery systems. So you can see here what now the system has been reduced. That is the we are going to have one PV cathode. In the B figure I am telling the PV cathode with the common anode and the battery cathode. This will act as an integrated battery design. Okay, this is called as 3 electrode configuration with common anode. Okay, whereas you can see figure or the same figure 1, see, if you see the figure C, we have PV anode negative ones and the battery anode with a common cathode. So this is called 3 electrode configuration with common cathode. Okay, so same as if we separate into come into 2 electrode configuration, that also we can possible, that is PV and the battery clubbed together as a cathode, as made it as one positive electrode, and the negative ones, that is the PV battery anode. This is called the 2 electrode configuration. So this is what the how the integration of both the generation and the storage device has been clubbed together. Okay, now you can see here the system has drastically reduced, and this only we have to see that how energy efficient, how the energy capacity and the density of this particular and the stability while clubbing these the PV batteries cathode as well as the battery cathode. Okay, this is what the traditional ones, which is A figure, that is the conventional discrete charging method, and which B, C, D are the our advanced integrated systems. Okay. So now in the advances in discrete PV battery systems, you can see here the PV batteries, the you know that the dominant material, what material the PV panels are made up of, that is the dominant silicon PV technologies is used for the battery charging. Since in the 2010 we have one module was been tested, which was directly charging the lithium ion batteries. So this lithium ion batteries were consisting of series strings of lithium iron phosphate cells. Okay, so each cell was having the 2.3 ampere hours rating. Okay, so in this there was no electronic devices were there, directly it is PV panels which is giving energy to the, or giving the charge, directly charging the lithium ion batteries. So this, when this test was carried, when whatever this model was derived, so in this the test was carried out as a proof of concept of solar charging of battery electric vehicles. Okay, so this was the concept they have made in the terms of charging the electric vehicle batteries. So we know that lithium ion batteries are the this particular electric vehicles are working based on the lithium ion batteries. So they have tested this. In this they have got that 15 cell of lithium ion batteries were modules were charging, obtained an overall efficiency, they got it as 14.5%. By combining the both 15% of PV efficiency and nearly we got, means they got that 100% electrical to the battery charging efficiency. They have tested this and they got nearly 100% electrical to the battery charging efficiency they have got by this connection of uh, one model, that is the, they have given the one model that is 190-watt peak panel, that is Sanyo HIP module, which is directly charging the lithium ion batteries. So next advancement came in the discrete PV battery system was using of triple junction solar cells stacks with a thin film solar cells. Okay, you can see here this particular triple junction is there in the figure B to D. So here we have seen that whatever the triple junction is there, it had a short circuit current density of around 2 milliampere per centimeter square, and the open circuited voltage of 2.09 voltage under the illumination of 37.4 milliwatt per centimeter square, which matched the exactly the battery characteristics. Okay, so this was the triple junction where they have created a stack like structure where the thin film of solar cells were being in the array of stack structure they have created. So this lithium ion battery, same, they were already been charging with this thin film solar cells. Okay. So based on this, the efficiency, how much the solar to the battery charging efficiency was around 8.5, which was exactly normally as same as the rating of the, or the efficiency when compared to the solar cell. So this was the leading to potential loss where the free energy transfer to the battery system they have recommended. Okay, so this was the next advancement, like going for the thin film in the triple junction solar cells, and which is going to charge the lithium ion batteries. Next came the material which was like emerging peroxide PV technology. This was being developed in this has also been investigated for the battery charging. So if we see for that in 2015s, there were 4 series connected PSCs, that is peroxide solar cells, were employed to charge the same lithium ion batteries. Okay, that provided the required charging of voltage, that is open circuit voltage of 3.84 volts and at the efficiency of 12.65 percentage. So this is that particular that peroxide material. This was the cells, peroxide cells, which is going to charge the lithium ion batteries. Okay, so this, whatever A figure and B figure, you can see here there are 4 peroxide cells are there, which is going to charge the lithium ion batteries. B tells this figure will tells the overall efficiency per cycle numbers. Okay, that is the per cycle of charging and discharging. Then C and D is the single junction. Whatever the four peroxide cells were there in that one particular solar cell single junction peroxide solar cells being charging the lithium ion batteries. This is the lithium ion batteries, and this is charged by the one single cell or single junction peroxide solar cell. So this was charging using a DC to DC converter. You can see here there is a one voltage boost converter is there. So which will be just a DC to DC converter for enhancement of the efficiency what they are getting from that particular peroxide. So this is the charging schematics, how it is being charging, and this overall efficiency when compared to the peroxides with the dye sensitized solar cells. You can see here there is red one which tells the efficiency when it was used as a peroxide solar cells charging the lithium ion batteries, and the dye sensitized cells or discrete solar cells. We can better to say that discrete solar cells having the or they're charging the lithium ion batteries. So you can see there is a huge drastic efficiency differences there, where you can get that discrete solar cells without any peroxides. We are getting only 5% of efficiency when charging to the lithium ion batteries. Okay, and then when using the peroxides we are getting 9% around charging, that is efficiency when charging the lithium ion batteries. So next comes the integrated PV battery systems. In this integrated PV battery systems, we are going to see that there are three ways by which we can realize these PV batteries of integrating the storage rather than capacitive energy storage rather than battery storage. So here we are going to only for going for to see with the capacitive energy storage when compared to the battery storage. So there are three methods are there by which we can design this particular PV battery systems. That is, the first one is the direct integration. We have photo assisted integration and the redox flow battery integration. This redox flow battery integration is the most trending research ones, because now uh, there is a huge heating problem which is going in across the electric vehicle batteries. Okay, so in order to reduce that heating effect, and you have seen that many road in means the news latest news also in when regarding the electric vehicles, that the batteries are getting exploded. Okay, it's getting blasted, or it can be due to the heat, that reactions they cannot take care. Okay, so that is what the redox flow battery integration is, the new research trending which is exactly going for the integrated PV battery systems. So direct integration, it will involve in the stack like structure where the solar cells and battery are clubbed together that can operate autonomously. Okay, so this which I have shown in the starting figure, that how these are solar cells and the battery together, they are going to stacked in the form of separately they are going to operate autonomously. Whereas in the photo assisted integration, in this they are using the photo charging to partially charge the battery. Okay, that means instead of direct, that is they are bypassing the solar cells and then they are partially charging the batteries with the help of photo charging. Okay, so and the third one, redox flow integration, it uses the redox flow battery with the photo charging. Okay, we'll discuss this one by one, how these advanced integrated advanced PV battery designs have been helping the energy efficiency of that particular, or increasing the battery efficiency life of that particular electric vehicle. Okay, so you can see here a direct integration. In this, the direct integration we have seen, you can see here this lights, as this is particular solar cells. Okay, this is going to be directly clubbed with the bipolar lithium ion battery. Okay, so this is a monolithically integrated design with crystalline silicon cells and the lithium ion batteries. You can see here this figure A, this particular figure A, you can see here these are clubbed, that is the PV module is going to be connected with the lithium ion batteries, that is bipolar lithium ion batteries, and these terminals which are coming out of this PV module and the positive terminal of the particular lithium ion battery has been clubbed together. Okay, so you can see here there is a negative terminal of PV and the lithium ion battery. This is the common battery. This is the minus. The plus minus is getting from the positive side of the silicon and negative side of the lithium ion batteries. So this is making as plus minus. And one while across the discharging, this same lithium ion batteries will be connected again with the positive charge when it is going to discharge. Okay, so this particular combination or the integration of lithium ion batteries with the PV module is enabling the use of aluminum metal electrode. This is, you can see here, lithium titanium with the aluminum metal electrode. This is the metal electrode which is coming out of the terminal by which you are getting at the time of charging and discharging. Okay, so this is what the how the direct integration of particular uh, lithium ion batteries with the PV module. Okay. And then this B figure will tells the efficiency of what is the storage efficiency and the capacity retention when we are clubbing these two directly integrated PV module with the lithium ion batteries. Okay, it's just the terminals only they have taken from the particular PV module. You can see from this particular blue, this A figure, this is the only the way how they are going to integrate the PV module with the lithium ion batteries. Okay. So in this direct integration, they have created a device which consists of 25 units of silicon solar cells connected in the series and a solid state lithium ion battery with a bipolar cell configuration that fabricated using the UV curing assisted printing process. This they have integrated with the help of UV curing assisted printing process, just like a printing that PCB designs, that how the cells, solar cells have been taken or in a form of printing process. So they have taken the terminals just like what you have been seeing the PCB in the same way printed circuit boards. So in that printed process only they are going to connect the terminals which is coming out of the PV module and the bipolar lithium ion batteries. So they have when they have clubbed these two directly, they got the overall efficiency as a higher as 7.6 percentage. You can see here this blue one, 7.6 percentage of the overall efficiency they got with a 15.8 efficient solar cell module. Okay, that means 15.8 percentage of efficient silicon solar modules have been we are getting as the efficiency for this particular solar modules. Okay, this is the how the direct integration of this particular uh, PV module will connected with the lithium ion batteries. So next they have in the same thing they have reported the series connected tandem dye sensitized solar cells. Now they have given the dye sensitized solar cells in which the top layer of the titanium foil they have created with the lithium ion batteries. Okay, so one side it is having the titanium foil, on the other side they are having the titanium dioxide nanotubes. Okay, so they have created a thin film which can be clubbed in the same way what it has been previously reported. Okay, so now they have clubbed this these two with the help of titanium foil on the top side of the lithium ion batteries, and the other side or the back side they have given the titanium dioxide nanotubes. Okay, so this integrated power pack was charged from 0.55 to the 2.99 second. It can see that how in 440 seconds only they have charged and they have got that around 2.9 or almost 3 voltage in the particular 440 seconds. Okay, so this device, when they are having the one like tandem, like continuous cascaded one, so in this they have got this device showed the capacity of 33 milliampere hours with a low overall efficiency of 0.82 and the strong storage efficiency of 41 percentage. Okay, so like this, if they can be for the huge scale, they can make it as a series combination in order to get the more that particular lithium, that is they can increase the current density, that is the milliampere hours ratings, they can be changed. So this is by the one particular module only. There we are just now from the one module with a thin layer, all these efficiency we are getting. Okay, so with this they have got the clear idea that how the, if they can get it as this, with a fraction of second from 0.55 to the 3 voltage in 440 seconds, then this efficiency is much more better than the previous one. Okay, so this is one technology what by which they have introduced the PV module with the lithium ion batteries with the help of titanium foil, with the one side on the top side, that is the dye sensitized solar cells, with the top layer of titanium foil, and the second layer as a titanium dioxide nanotubes. Okay, another, they have come up with the another design in which the platinum, integration of platinum modified as the cadmium selenium photocatalyst into a hybrid lithium sulfur batteries. Okay, so this particular ones, when they have reported that we can integrate the platinum with the cadmium selenium photocatalyst, in this they have got that they can increase the charging or the specific capacity of the charging this particular lithium ion batteries was more. Okay, so you can see that, however, we can say that one requirement for this type of design is the cathode, whatever is there, must be directly oxidized, okay, by the photo excited holes in the photoelectrodes. Okay, so this, by integrating this particular platinum modified cadmium selenium, this limits the scalability of this design. Because why? Because the most of the cathode materials for conventional lithium and batteries are insulating, okay, and insoluble in organic or aqueous electrolytes. So this particular design with the platinum as a modified cadmium selenium, that particular electrolyte, so this cathode has whatever the conventional lithium ion batteries are there the electrolytes will be more showing the insulating, okay, and insoluble in the organic, because we don't want more, we want more reactions within the lithium ion battery so that they can get more charging, or the charging storage capacity can be increased. Okay, so this was the direct, this particular integration of platinum modified. However, the percentage and the discharge capacity, so this discharge capacity of 288 milliampere hour per gram, that is upon exposure to the sunlight for 2 hours. So this was the you can say that practical feasibility of design was not that much efficient when compared to the previous ones. Okay, then recently in the direct integration, they have gone with the two electrode photo rechargeable lithium ion battery enabled with the direct photo oxidation of lithium iron phosphate nanocrystals in the form, in the presence of dye. Okay, dye is a material where the hybrid cathode and the lithium metal as anode has been created. So you can see here this figure C. This figure C will tell you the how the lithium batteries, that is photo rechargeable batteries, they have created. Okay, that means they can use the direct photo oxidation of lithium iron phosphate nanocrystals in presence of dye as a hybrid cathode and the lithium metal. So here the overall efficiency of the system around was 0.06 percentage to 0.08 percentage. So what happened in this particular this nanocrystal lithium iron phosphate nanocrystals in presence of dyes, this dye generated the number of holes enabled the delithification of lithium iron phosphate. So what it does, in the presence of dye, whatever the positive holes were there in the p region of the batteries of the PV, they have removed this lithium from this particular electrolyte, lithium iron phosphate, and it is converting into iron phosphate. So whatever the electrons were there, these electrons enable the reduction of oxygen, forming the peroxides and superoxide. That means only they are going to have the carbonate based electrolytes to form the solid electrolyte interface. Okay. So this was the layer which was in the lithium oxide batteries. So it is very much here. One interesting note was that photo charged batteries was kept open in the uh, or you can say that it was getting the illumination during the discharging process also. So when discharging, they have demonstrated the discharging capacity of 340 milliampere hours per gram. So this particular surface area, whatever the surface area of lithium iron phosphate nanocrystal was found to be the dominant factor facilitating the delithification process. And further, they have shown that this particular photo oxidation only worked in the presence of oxygen. So whatever the design requires, it requires the interfacial engineering of lithium iron phosphate with the diphoto cathode to reduce the charging, recombination losses and improve the efficiency. Okay, so when you if you give more photo oxidation, that means photo oxidation means it will require the oxygen. Okay, so since you have removed the lithium from the iron phosphate, now only thing part was left with the iron, that is the iron which is getting from the oxygen. Okay, in the presence of oxygen, it worked, and there is a engineering design is required to interface these lithium iron phosphate with the dye. Okay, so this cathode was reduced charge combination because there was no charging recombination happened, and this charge recombination loses this and improves the efficiency if the number of charges have been removed. So that means recombination process they can improve, and then the efficiency, overall efficiency can be increased. Okay, this was the direct integration process when discussed in terms of stacking the solar PV module with the directly with the bipolar lithium ion batteries. Okay, so this was whole process where when required for the direct integration. Okay, so these are the recent advances in the discrete, that is in the integration process of PV module with the particular lithium ion batteries, because our main motive is how efficiently we can charge this EV batteries with the PV module or the PV batteries. Okay, so both the PV batteries as well as the lithium ion batteries are stacked together to form the direct integration. Okay, so next comes the photo assisted integration. In this photo assisted integration, this PV cell is integrated with the battery storage to assist the battery charging. You can see here in the first figure, that means this photo electrodes are there. They are kept like a photo electrodes. Okay. And this electrolyte, because they wanted to create the electrolyte with the lithium ion batteries. So this primary objective of the photo assisted charging is to reduce the high charging voltage of the batteries and consequently the over potential losses. Okay, so because if you keep on charging the lithium ion batteries, keep on charging, which is not recommended, so we require this photo assisted. It will definitely reduce the high charging voltage to the batteries. Okay, so because of this, we can, the loss, overall potential loss has been reduced. Okay, so this is what, how the photo assisted for charging is been done. We have the photo electrodes. Okay, in this you are going to have the metal oxide and metal reduction, metal oxidation, and the metal reduction will be going to happen. And then this, whatever the photo electrodes are there, it is going to be connected with the lithium anode. So positive is connected with the photoelectrodes, and the negative one, which is going to be connected with the lithium ion batteries, where the lithium anode has a negative potential. Okay, and the cathode is being kept, and there is a separator between, because we know that lithium ion batteries will have both the electrodes, cathode as well as the anode. So cathode is separated with the anode, and then when the first charging happened to the anode and discharging, so it discharges the particular electrons from the lithium anode to the cathode. Okay, so this is how the photo assisted integration is there. We are directly, the photo electrodes are there, which is going to be illuminated, gets illuminated with the directly from the photons. So this photo assisted charging was employed in the lithium air batteries by integrating the dye-sensitized titanium oxide photoelectrode with the oxygen electrode via the linkage of triiodide or iodide redox shuttle. So this figure A was the dye-sensitized titanium oxide photoelectrode is there. Okay, whatever the photo assisted integration in this photoelectrode was made up of dye-sensitized titanium titanium oxide with the oxygen electrode. Okay, so this will be acting as our the first positive um, charge from the dye-sensitized titanium oxide. So when in under the direct illumination of the solar cell, whatever the photoelectrode generated inside this particular electrons or the triiodide, okay, these ions will be separating from this particular titanium oxide. So it will comes around triiodide. Okay, ions will be there that subsequently diffused to the oxygen electrodes to oxidize lithium ion or lithium peroxide. Okay, so this, whatever the combination of this photo assisted is there under the continuous illumination. So this particular iodides, the triiodide ions will be diffusing the oxygen electrode, and then it is oxidizing the, to get it at oxidized lithium peroxide. So this charging voltage was reduced from 3.6 to 2.7. You can see here from the figure B, this is the solar battery, which is denoted by the pink color. This blue one is the lithium oxygen, that is the lithium air batteries with the lithium iodide redox shuttle. Okay, so you can see here the charging voltage has reduced from 3.6 to 2.7. However, the cell exhibited the voltage instability with the cycling. You can see here, whatever the cell voltage was there, due to the illumination of drop of 0.7 volt, it has reduced to 2.78 voltage. Okay, so the charging voltage was only the reduced, which we have seen from this particular photo assisted dye sensitized titanium oxide was there. Next, in some of the other cases, they have used the titanium oxide photoelectrode coupled with an iodide. Now instead of we are using here, they are using the dye sensitized iode with the oxygen. So here we are not using with the oxygen, we are only we are photoelectrodes coupled with the iodide. Okay, so this ion redox shuttle in the lithium iron phosphate figure, you can see here this part, the photo voltage reduce the solar cell charging to 2.78, same way what we have discussed, which was lower than the discharge voltage of 3.41. So you can see here there is a drastic change is there. How much the discharge voltage, which was previously at 3.41 voltage, now it has leads to the 2.78 voltage. So it leads to an energy saving of 20%. Okay, so you can see here that much we want to save our energy, so the discharging voltage has been reduced, so we are getting at least that particular savings in the energy. So same way, a similar work was also been shown in while integrating the dye sensitized photoelectrode in a lithium iodide redox flow batteries with the linkage of iodide based catholite. Okay, so in this, however, we have seen that, however, these whatever the photo assisted integrated systems are there, still it requires an external charging source to fully charge the batteries. Okay, so since whatever the reaction it is going inside the batteries and the photoelectrodes, still it requires the external source by which the batteries can be get fully charged, so which does not make them an energy self-sufficient integrated design. Okay, so when they have seen this lithium iodide redox flow batteries, the charging voltage was reduced from 3.6 to the 2.9 voltage. Okay, so these are the some of the photo assisted charging approaches are there. Okay, so by which we have seen that what all the uh, reactions, how the lithium ion batteries are being charged with the help of photoelectrodes rather than we are using the silicon cells. So here we are not using any silicon cells, we are directly using the photoelectrodes which are equivalent to the solar cells, and there we have seen that discharging voltage has been reduced. But wherever you are seeing that in order to charge the batteries at a full capacity, it still requires the external charging source. Okay, because that particular photoelectrodes cannot be charged the sufficient batteries of the lithium ions, and because of that only it is not come under the self-sufficient integrated designs. Okay, so next comes the redox flow battery integration, where this redox flow batteries have gained the attention. How they have got the attention? Based on their flexibility, scalability, high lifetime, low operating cost, and the potential to store the energy in the large amount. So this is the which I told in the beginning also, that we are having the um, research trends which are showing the high potential to store the excess amount of energy, that is only possible with the help of redox flow battery integration. So these attributes, whatever I have just now told, that is flexibility, scalability, high lifetime, low operating cost, and the potential to store the abundant or the large amount of energy, makes the redox flow batteries competitive with the lithium ion technology for a large scale grid storage. Okay, this is going to be happen because we cannot store much energy in the lithium ion batteries. We have to go for the redox flow battery design, where this particular batteries can be used for the large scale production. Okay, So this is the typical redox flow batteries shown in this figure. You can see here it consists of two compartments of redox electrolyte separated by a membrane. This is the membrane. They have external cathode, okay, and the external electrolytes. So this, in between these two, there is a membrane and a pumping electrolyte through the cathode, that is called catholyte, and anode is there. In this anode is there. This will act as a anolyte that is stored externally. Okay. So here you can see here this particular, whatever the triiodide or iodide redox reactions are there, this triiodide or the redox couple is the most commonly studied catholyte in the solar redox flow batteries. Okay, so whatever this triiodide or the iodide redox coupled with the catholyte, okay, this was getting the uh, advancement in the charging and the discharging also. The rate for discharging is very less, so you can have the much more weightage of the storing the charges. Okay, if the discharge rate is less, that means the storage capacity is been more. So one, they have used the titanium oxide dye sensitized for charging the redox flow batteries with two redox couples, that is iodide or the triiodide or the iodide and the direct DMCs. Okay, there the metal cooperated with the iron or the inorganic solvents. So in this particular ones, you can see here whatever the charging or the overall efficiency with the one complete cell of one photoelectrodes, this particular cathode, when, because external charging is required for the redox flow batteries. So this they have taken with the combination of dye sensitized titanium oxide for charging the redox flow batteries, which is going to be coupled with the redox flows. That means triiodide or the iodide couple. With this, they are getting the charging of how the lithium ion batteries ions can be stored. Okay, that means now we this particular, they have got the efficiency around, overall efficiency of around 0.05% with the 0.15 photo conversion efficiency of dye sensitized solar cells. So they are only using the 0.15 percentage of photo conversion has been occurred. So you can see that overall efficiency in terms of charging and discharging is around 0.05 percentage. Okay, that means this is good for that demonstrating the particular charging, okay, of the redox flow at this 95 percentage or the 99.05 percentage. Also we are having the uh, capacity of charging is more while in terms of discharging. Okay, so when it comes to the dye sensitized solar cells, the area and the thickness of organic separator led to the large internal resistance and thus low efficiency. Okay, so in this, one author which is investigated the solar rechargeable redox flow batteries where the lithium tungsten oxide couples in a dual phase electrolyte disensitized titanium as a photoanode soluble in the electrolyte of lithium tungsten oxide as a anode active species in the aqueous electrolyte. Whatever the lithium iodide was there as a cathode active species in the organic electrolyte and the lithium superionics conductor glass ceramics as a separation of the membrane. So this, whatever the membrane you are seeing, it is made up of the combination of lithium tungsten oxide, okay, with the dye sensitized titanium oxide as a photoanode. So whatever the photoanodes are there, that is will be the dye sensitized titanium oxide, and the electrolyte will be the dual electrolyte based on the lithium tungsten oxide. So this they are going to separate with the lithium iodide as a cathode, and the lithium ionic or the superionic conductor as a glass ceramics as used as a separation of the membrane. So in this you can see here from this figure, the discharge capacity of 0.0195 milliampere per milliliter at a current density of 0.075 milliampere per centimeter square is shown from this particular figure B. So photo charging is around zero point 0.6 in 10 minutes, and then discharging you can see from 10 minutes to around 0 to 10 minutes the discharging rate was very less. So as an alternative, the solar rechargeable vanadium redox flow batteries are demonstrated by integrating the titanium oxide. So in this, there were the one-dimensional titanium oxide nano belts are there as a photoelectrode into all vanadium 2 redox couples. That means vanadium oxide plus vanadium oxide and the three more vanadium plus V2 separated by the sodium fine membrane. That is, uh, this is the membrane which they have used for the vanadium redox reaction. Okay, so they have used the titanium oxide with a large band gap, which if they are using the large band gap means they are limiting the light absorption. Okay, that means with the help of aqueous compatible redox couple, it has an advantage of higher working voltage and low fabrication cost, and also it is environmental benign. Okay. However, this whatever the solar rechargeable iodine based redox batteries are there, they have the limitation as low energy storage capacity, insufficient light absorption, and corrosive iodine based catholites are the some drawbacks of this particular solar rechargeable based iodine based. Okay, so iodine based, obviously as there is a insulators are there, that means the band gap of between this light is very less, means light absorption is very less. Okay, so because of this, their demands this situation, whatever this situation demands further advancements, because they don't want to go for the uh, insufficient light absorption, because overall efficiency of the sol or the cells or the solar charging batteries reduces because of large band gap. Okay, so there was another study which shows that uh, integration of tungsten oxide decorated with the titanium oxide to enhance the light absorption of the photoelectrode and promote the extra energy storage. Just to provide more extra energy, they are uh, clubbing the tungsten oxide with the titanium oxide. In this particular use of acidic media for vanadium redox couple limits the selection of wide range of light absorbing materials, because when you are using the vanadium material, it will reduce the selection of the light absorbing materials. So alternatively, if you go for lower band gap polyanyl polymer deposited hematite as a photoelectrode was studied in the combination of redox couple aqueous solution of ferrocyanide or disulfonate in the sodium hydroxide to enhance the photovoltage. So they have clubbed some of the aqueous solutions of ferrocyanide, disulfate, sodium hydroxide to enhance the photovoltage. So this low band gap semiconductors such as silicon and gallium arsenide are the most suitable candidates for the efficient light harvesting, because since the recently solar recharger flow was developed based on the dual silicon photoelectrochemicals. Okay, based on the quinine bromine redox flow batteries. You can see this C section and the D section, which shows the charging and the discharging of the particular redox coupled batteries. So this device, whatever this photoelectrochemical with quinine bromine redox couples, they have shown the overall efficiency of around 3.2 percentage, as you can see from this figure, that outperforms the other reported solar rechargeable flow cells. So if we use the narrow band gap silicon for efficient photon collection and the fast redox couples for efficient charging transfer at the interface where they're responsible for the high efficiency. So this device can only be producing the photo charge to the zero point 0.8 volts, demonstrating the discharge capacity of 730 milliampere hours per liter. Okay. So these were the overall recent trends, what all the efficiencies when compared to the conventional batteries with the separate photovoltaic cells is being overcome with the help of integrated designs, where we have seen the direct integration, photo assisted integrations, and the redox flow couples. Okay. So technical challenges and opportunities are like capacity or energy densities. So we have seen that lithium ion batteries are traditionally packed like jelly rolls. You can see that as a jelly they will be designed. So where anode and cathode are stacked together, okay, with a polymeric separator and encapsulated with the metal laminations. So this architecture provides the battery with a high capacity, that is milliampere hours ratings, and energy density, that is watt hour per liter. Use of material with a high specific capacity is one of the solutions. We have seen that in the redox flow equation, where redox flow couple batteries, they are using the material with a high specific capacity. Then silicon and metal carbonate batteries have been using with a high energy density of 4000 watt hour per kg. So another potential anode material is the lithium metal, which can deliver the high energy density at around 500 watt hour per kg with NMC cathode. In addition, we can go for lithium doping in the peroxides, which have been shown the positive effects of enhancement in the PV performance. This makes the peroxides a suitable candidate with a high capacity bifunctional material for the integrated PV battery designs. Then we can go for the overall efficiency. So overall efficiency, you can see here the overall efficiency of integrated PV battery devices is only 7.6 percentage for the 3 electrode directly integrated systems, 0.08 percentage of 2 electrode directly integrated systems, and 3.2 percentage of the redox flow integrated system. So the overall efficiency of the integrated PV battery system is a product of photoelectric conversion efficiency of PV and energy storage efficiency of the battery. So the maximum overall efficiency is the photoelectric conversion efficiency of the photovoltaics, because how you are going to convert, if how much efficiently you can convert this efficiency of getting the solar cells from the PV, then only that efficiency will depends on. So you can see here from the figure also, overall efficiency percentage has been increased to around 24 percentage, that is shown by the around 21 to 24, that is uh, multi silicon cells, which shows the 22 percentage of efficiency. Then peroxide solar cells also shown a very nice, very better efficiency, that is around 20.9. So peroxide material with the redox flow is the trending one, or we can say that these are the materials which they have shown the high efficiency of the PV. Then in terms of stability, stability is a concern for any new energy technology, whatever the new technology it is being and incorporated. How much scalability and the stability of integrated PV battery systems mainly concerns the photo stability, electrochemical stability, and environment stability. Here, stability also plays a vital role in the material selection. How much of selecting the material will play in determining the stability. And it should be noted that the integrated PV battery system will be benefited from the advances in the stability that take place in the PV and the batteries individually. So in terms of, if I say that there are other aspects of integrated system is the MPPT. So PV panels are connected to the power electronics units with the charge controllers and inverters that are also incorporated with the MPPTs. Integrated PV battery designs might not offer the flexibility of power tracking into it, since the scientific approach would be to properly match the voltage and current between the PV module and the batteries. For maximum overall efficiency, the integrated PV battery cells need to be operated at the maximum power point of the PV cells. Okay. So this was all about the trends or the advancements in the PV batteries when connecting with the electric vehicle batteries. Okay. So thank you so much for giving me this opportunity to share my thoughts on this advancements in the batteries and the solar photovoltaics integrating with the electrical vehicles. If you have any doubts, if any participants have any doubts, platform is open. You can ask any doubts regarding to this. Sorry?
Here, why is here, sir? How are you, sir?
Ah, fine, sir.
Sir, I can ask one question, sir.
Yeah, yeah, sure, sir.
Sir, what will be the size of that battery, sir?
Size in terms of,
According to their power, sir,
it depends on the energy capacity, sir.
capacity.
Ah,
Means,
in terms of
oh,
how much particular energy density or energy capacity you want to create, that much cell size will be more.
okay. Thank you, sir.
Okay, sir. Any further doubts? Okay. So we'll have a short break uh, of 10 minutes. After this, I will resume back after 10 minutes regarding the advancements in the power electronics applications in the solar photovoltaics. Good evening, everyone. I hope my screen is visible to everyone, right? Can I get the confirmation?
Yes.
Yep, it is visible to everyone.
Okay, thank you, sir. So, welcome you all once again for this ATAL FDP. So, the next session will be on the advanced power electronics for the solar photovoltaic systems. So, in this, what are the power electronics applications? What are the power electronic converters are there which we are using for the solar photovoltaics? I will be discussing on that aspects. So before starting this, I will be going through the different contents. First, I will be discussing about the general description of what is the requirement of electronic devices, advancements, then photovoltaic system configurations, and then we are going to see the power electronics topologies. In this, we are going to see single phase, single stage, single phase, multi-stage, and three phase. And then last but not the least, I will be discussing about the generalized power electronics and control. So in the general description, as we all know that for a PV system, we require the constant voltage output as DC, whose magnitudes depends on the configuration of the solar cells, the way how they are connected. And on the other hand, we have seen that current output of the PV system is also important, which primarily depends upon the solar irradiance. So the main requirement, since we know that only voltage and current is required, then what is the requirement of Poltronics? So the main requirement of the Poltronics interface for the PV system is to convert the generated DC voltage into a suitable AC for a consumer use and the utility connections. Okay. So when you are connecting with one lower voltage into the higher voltages with the AC, with the frequency involved in this, then the Poltronics devices or the converters are come into the picture. And due to that part only, there will be some power quality issues or the harmonics, the ripples, how these can be avoided when compared to the advanced Poltronics devices. So generally the DC voltage magnitude of the PV array is required to boost a higher volt value by using the DC-DC converters before converting them into the utility compatible ACs. As I said just now, that how these are connected with the going to have the higher voltages. So when compared connecting to the AC voltage, it requires the first thing is we should come across the compatibility of connecting with the or achieving the higher voltages at the AC side. So before connecting it, we require the higher voltages, values of the voltage, which can be only get with the help of DC-DC converters. Okay. So the DC then once it requires came the configuration achieved with the higher voltage, the DC to AC inverters are then utilized to convert the voltage to the 50 hertz frequency of AC. So the process of controlling the voltage and current output of the array has to be optimized based on the weather conditions, because you know that the output of the DCs, that is a photo PV panel, is not constant. We have to go through the to achieve the constant voltage. It requires the proper optimization. Okay, so that optimization of depends on the weather conditions, how the weather conditions playing in the vital role. So based on that, we are going to have the respective maximum peak where we are going to get the optimized voltage and currents. So the specialized control algorithms have been developed in the form of MPPTs. This is the algorithm which works on the maximum power. We are going to get at the maximum power what is the voltage and current we are getting in order to constantly extract the maximum power from the array under the varying conditions. Okay. So there are number of algorithms are there, why that is starting from the generalized conventional algorithms like perturban. The most common one is the perturban observe. We have incremental conductance. We have voltage based um, integrations. Then we have, when we got for the AI based, so their artificial intelligence based designs are also there. Okay, so which can be done with the help of MPPT's algorithm by varying the optimizations. We have bio inspired algorithms are also there in the MPPT. So this MPPT control process and the voltage boosting are usually implemented in the DC-DC converter only, whereas DC to AC inverter is used for the grid control current method. Okay, so if I go with the photovoltaic system configuration, in photovoltaic system configuration, we have seen that PV modules are connected together into arrays to produce a large amount of electricity. There, the arrays is then connected with the system components such as inverters or the inverters to convert the DC power into the AC electricity for the consumer use. So the inverter of the PV system performs many functions, like it converts first DC power into AC. It also contains the protective functions that monitors the grid connections and the PV source and can isolate the PV array if the grid problem occurs. So the inverter, whatever the inverter is there, this monitors the terminal condition of the PV module and contains the MPPT for maximizing the energy capture. So this MPPT maintains the PV operation at the highest possible efficiency over the wide input conditions, because it is going to be vary according to the season, from morning to noon, noon to evening, and then seasonally, like winter season, what is the variation, what is the variation in the summer seasons, so that it is going to optimize at that single point only. We are going to have the particular maximum power point. From there, you can get it as the how we are going to get it, or where from which parameters and how the parameters are going to be optimized, that we have to take care. Okay. So in the generalized photovoltaic system configuration, this is the centralized PV connections, how the PV panels are connected in the series with the parallel to achieve the particular voltage. So each configuration has the basic powertronic interface. You can see here, this is the way the centralized converter powertronic configurations that interface the system with the utility grids. So this is the centralized inverter is used from here. So this converts the DC to AC part. So this has been the most common type of PV installation in the past, and PV modules are connected in series and as connected in this particular figure. So this photovoltaic system configuration shows this particular ones, that is the PV panels in string with the individual inverter. So what we did here, this is, say suppose this is my string 1, it will have its own single inverter, and the string 2 will have its own another inverter. So what is the primary advantage of this separating the single string with the individual inverter? So this primary advantage of this topology is that there are no losses associated with the string diodes. Because if you see here, there are string diodes are there. Okay, this is unidirectional ones, so that the leakage currents or it cannot come back to the solar. So here that problem is going to be avoided. So there are no losses associated with the string diodes, and the maximum power point tracker can be applied for each string. This is especially useful when the multiple strings are mounted on a fixed surface in different orientation. So there we can use this. This is the best way to use this multiple strings with the individual inverters. The only disadvantage to this configuration is if you are separating this individual strings and you are putting more and more inverters, definitely the cost of additional inverters has been increased. Okay. So this is the PV panel with the individual inverters. Now we have PV panels in a multi-string configurations. Now in the multi-string inverters, you can see here, this is my DC-DC multi-string with the DC-DC converter and DC-DC-DC converter, and then we are having the common inverter. Okay, so in multi-string, we have seen that there, you can see from this figure that there are several strings that are interfaced with their own DC-DC converter. Like this string converter will have its own DC converter for voltage boosting, and are then connected to this, whatever the voltage booster is coming from this particular first string, it is going to be getting the voltage boosting at this particular common DC bus. This is the common DC bus, and then the common DC to AC inverter is then used for for interfacing with the utility. Okay, so the input voltage coming from the PV string may be high enough, because whatever the input voltage which is coming from the PV strings will have definitely high enough to avoid the need of voltage amplification. As the cost of PV module is still rather expensive, the voltage amplification can be added together with the string inverter in order to allow for the fewer modules to be connected to the inverters. Okay. So now,
Sujit Kumar, I have one question, Dr.
yes,
Sujit
sir.
Kumar.
Yes, sir.
Just in the previous slide,
This one?
yes. So you are adding the boosted DC voltage. Okay. But in fact, you see that here they are connected in, I think so, parallel or in
Yes,
series.
sir. Sir, they are connected in parallel only.
Parallel then means the voltage is same. The boosted voltage is of the same level, both the
Yes.
strings.
Yes, sir.
Okay, fine. Each string is being boosted, and then
Boosted.
they are connected in parallel.
Yes, sir.
Okay. You can proceed further. Thank you.
So next we have the AC module power electronic configuration, where in this particular one, like this is one complete AC module 1, module 2, module 3. So this configuration where each module will have its own inverter. So this design is also known as I said, discussed, this is the AC module. It is having the high flexibility and the configurable design topology. However, the previous examples of these configurations and configuration are still more costly than the conventional PV system, because you are creating one by one inverter with the PV panel with the separate inverter modules. So advantage of this type of system is that it is easy to add the modules, because each module has its own DC to AC inverter, and the connection to the utility is made by connecting the inverter AC field wires with wiring together. So there is also an overall improvement in the system reliability, because there is no single point failure for the systems. Okay. So this is what the configuration of this particular AC module Powertronics. So now when we go for the Polytronic topologies available to us, we are going to have the first topology, that is single phase, single stage. So this Polytronic topologies for the PV system can be categorized on the basis of number of power processing stages, the location of power decoupling capacitors, and utilization transformers, and the type of grid interface. So the most fundamental topology for the PV inverter is the single phase self-commutated PV system. As you can see in this particular figure, the DC output of the PV array is connected across the filter capacitor. Okay, so this capacitor is used to limit the harmonics currents in the array, and this output of this capacitor is connected to the full bridge converter. And then from here you can see the output of the converter is connected to the inductor, which limits the high frequency harmonics injected into the AC systems. Okay, so this is one advantage of how the single phase single stage converting stages are being provided. So this particular stage, whatever is there, it's having the only one complete inverter, that is a DC to AC, where we are using the LC filters and the capacitor filters, which we are getting just immediately after the PV panels. Second one, that is the single phase multiple stage. In this, to avoid the bulkiness of this topology of the prior topology, the low frequency transformers, which are regarded as the poor component, mainly due to the relatively large size, okay, and the low efficiency. So this multi-stage, that is two-stage conversion systems, are widely used for the PV generations. So you can see here in this, what we are going to do, we are going to have a DC to AC grid connected voltage source with the help of pulse width modulation inverter with some kind of same DC-DC PV connected converters. So in general, what DC-DC converter performs, that is the boosting of voltages and performs the MPPT technique. So perhaps the voltage amplification, we still requires the MPPTs, and then the DC to AC full bridge inverter controls the grid current by means of PWM or the bang bang operations. Okay, so just to avoid the huge bulkiness of the transformers, that is low frequency transformers, we are regarding as the low efficiency, and to avoid this low efficiency, we are going to use for the multiple stage, that is two stage conversions. This is what the single phase multi stage. You can see here, this is the high frequency transformers are there. Okay, so which in this high frequency transformers are connected between the one switch inverter module when it is converting to the diode bridge rectifiers. Okay, this is called your single phase multi-stage PV converters. So this is my thyristor gate circuits. Okay, and then you are connecting to the utility ends. So in multi-stage, the DC voltage input is inverted to the produce high frequency AC. Whatever the DC input, what you are getting from this is going to invert to produce the high frequency AC across the primary of the high frequency transformers, and then the transferring secondary voltage is rectified. Okay, then the resulting DC output is interfaced with the line voltage through the line frequency line voltage commutator thyristor inverter. This is what we have given. Okay, so after this, the whatever the line current is required to be sinusoidal and in phase with the line voltages. So the line voltage waveform, whatever you are going to measure, is in the reference waveform of the sinusoidal line current, whose amplitude is determined by the peak power tracking controllers. So this inverter can be controlled using the current regulated current controllers. Whatever you are seeing here in the multi-stage, these are all current controlled devices. Okay. So next comes the three phase. Here you can see here, whatever the DC output of the PV array is connected across the filter capacitor, the output of the capacitor connects to the input of the voltage, that is the voltage source three phase inverter. This is whatever the output of the DC, this capacitor is going to be connected across the three phase inverters, that is voltage source three phase inverters. So the output of each phase, the output of each phase of the converter is connected to a inductor, that is from between these two rectifier thyristor based inverters, going to be connected with the inductor and the capacitor. So we are using this inductor and the capacitor to limit the high frequency harmonics injected into the AC system. So whatever the synthesized AC output voltage is produced by appropriately controlling the switches, we can control the switches, and then synthesized AC voltage can be get. A three-phase transformer is then used to connect the power utility to this from the PV panel to the utility ends. So this is the generalized three-phase powertronic topologies what we are going to use. Then there are separate different configurations that can also be used without transformers with the you can say that without using the transformers also you can use these topologies. Like these topologies are more utilized in the European countries and Japan. Why? Because there the grounding system is not mandatory for PV inverters. But in India, it is mandatory to provide the system grounding. So there itself we require the transformers, three-phase transformers. There we can go for it is mandatory for the PV inverters. So whatever the modern inverters we are using with the high frequency transformers, they are used for the galvanic isolations. Okay. So this technology, whatever is there, is going to be reliable, entirely new design, and can be integrated with the magnetic circuits. So this whatever the as I just now said, the modern inverters which they are using with the high frequency transformers. So in this galvanic isolation, if I tell that it is just a principle of isolating the functional selection of electrical systems to prevent the current flow. That means there is no direct conduction path is permitted here. Okay. So whatever the energy or the information can be still exchanged between the sections by other means, such as capacitive, inductive, or optical, acoustic, mechanical, like this, they can go for it. So this modern trend, modern inverters are equipped with the high frequency transformers. So one such design is shown here where we are using the transformers which are embedded in the high frequency DC-DC converters. You can see here, say suppose this is my string 1. This is my DC converter with the high frequency transformers connected with the common DC bus. You can see here string 2, string 1, like this parallel strings you can connect with a common DC bus. So this type of topology is also very useful for multi-string configurations, because where each of the strings can be connected to a common DC bus. And then we can convert to the grid compatible AC by using the single DC to AC inverters. Okay, so this is what we are using the high frequency embedded DC-DC converters. Okay, with the help of high frequency transformers, which are in the form of galvanic isolations. So generalized powertronics and control methods are there. If I show that while incorporating all these powertronics converters, okay, we have different means MPPTs which and with the voltage boost are done by the DC-DC converter itself. So the power flow control to this utility and the sinusoidal unity power factor current injection to the utility is produced by the DC to AC inverter controller. From the previous subsection, you can see here, it can be observed that the most generalized form of powertronic topology of the PV application is your DC-DC converter with the embedded high frequency transformers along with the DC environment, DC inverters. So in this particular figure, you can see that whatever the powertrain shows in this particular figure, that is having the DC-DC converter and three-phase inverters. You can see here DC-DC converters and then three-phase inverters. So this three-phase, whatever the DC converters are there, these are based on the current source full bridge inverters. Okay, whatever we are shown here, you can see here all these are based on the current source controlled devices, that is full bridge inverters with an embedded of high frequency transformers and rectifiers. So whatever the inverters are there, these are also the galvanic insulation isolation between the PV string and the grid. So these PV strings can be easily grounded, and then the current source input stage, it can reduce the requirement of filter capacitor, because in current source control devices we don't require the additional filter capacitor in parallel with the PV strings. So this part we have removed from this for the current source. In the next beneficial stage only, I am telling the filter capacitors are not required. So furthermore, the diodes included in the rectifiers are the current commutated, involving the low reverse recovery of the diodes and the low voltage stress. So in this particular figure 8, effective methodology of MPPT is shown here. This particular voltage from the PV string is first converted into high frequency AC. Okay, then with the help of galvanic isolation with the voltage boosting, it is accomplished through the use of high frequency transformers. This is the high frequency transformers. Okay, and the transformer secondary is connected to the rectified full bridge diode rectifiers, and then the rectified DC is then converted into grid with a compatible AC and converted into utility by three-phase voltage source inverters. Now you can see here some other effective method of MPPT is shown here by measuring the string voltage. Whatever the string voltage is there and the current, the PV array output power is calculated and compared with the actual one, actual PV array output power. Okay, so we are going to compare. Depending upon the result of the comparison, the duty cycle is changed to control the input current for the current source inverter. Correct? So now what happens, whatever the mismatch or the power which is actually getting from the PV and which is getting from the calculator one. Okay, so this process is repeated until the maximum power point has been reached. Okay, so we'll keep on changing the based on the power we are going, duty cycle has to be changed accordingly when you are controlling the input current. So other types of MPPT controllers can also be developed within the same controllers. Like additional controllers can also be designed to control the amplitude of the high frequency AC voltage at the primary of these transformers. Okay, that means whatever we are going to high amplification or the high frequency AC voltage, you can have the additional voltage also. Okay, so this high additional voltage can be done with the additional controllers can be put, and based on this you can vary the duty cycle in such a way that it is going to get the maximum power point with the lesser power also. Okay, now there are two ways of controlling this mode of grid connected inverters. One, you can do it with the help of current control, and the other is done with the help of constant power control. Okay, whatever the figure this was there, this is based on the current control. So the control of, that is shown in the help of constant power control. In this, whatever the inner central loop you are seeing, this one, all the power regulators, current regulators, this inner central loop regulates the current and the other control loop regulates the power. You can see here, this particular one is the power regulator and this one is your regulated current control. Okay, so when you are going to, in some cases where the reactive power reference, where the reactive power Q reference could be the power factor reference. So there the power factor reference we are changing. So based on that, the reactive power reference, how much the AC side power factor has been developed, so that we can change so that the voltage profile has to be maintained at the AC side. So by controlling this reference, the injected current at the utility can be maintained at the unity power factor. Okay, so uh, whatever the currents you are going to inject in the AC side, okay, that can be maintained at the unity power factor by varying the reference Q reactive power at that particular uh, point. So as the variation of constant power control can be implemented to maintain the DC bus voltage at the constant value. So it is still a debate that if an inverter should be allowed to regulate the voltage during the grid connected operations, because when you connect the inverters, because at the we are going to regulate the voltage during the grid connected operations. So it's a very huge task that inverter has to regulate the voltage every time. According to the current IEEE 1547 standards, it doesn't allow the distributed generation to actively regulate the voltage. Okay, this is actually what, when we go for the simulation, okay, we are not bothered that much that active means regulated voltage supply can be changed with the inverter. But when you take according to the IEEE standards, it is not allowed, not at all allowed also. Okay, so while some people in the industry suggest that voltage regulation may have some positive impact on the grid also. When it comes to the constant power control, in this case, the active power, that is the P reference, you can see here, this P reference active power can be replaced with the VD reference. That means regulated voltage supply. And the P out can be replaced with the V out. Whatever this regulated power supplies are there, if we replace this P out with the voltage D out, okay, there then the DC, so that DC voltage is regulated to the set point of the VD reference. So whatever the output of this outer control loop is set point, this ID, whatever this ID reference is there, this can be regulated. Okay, this can be regulated, and as a reference signal, this can be given to the current regulator. Okay, so this is how the constant power control can be replaced with the help of DC voltage reference. Okay. So whenever the DC voltage bus is increasing, meaning is the power from the primary source is increasing. Whatever the DC bus voltage is increasing, we are saying that the power from the primary source is increasing. Therefore, it is charging the DC capacitor more. So in order to maintain the DC bus voltage, whatever the ID was there, ID will be increased so that the power can be transferred to the inverter output. Okay, that is what the set point of the inverter, which is referred to the signal of the particular current regulators. Okay, so these are the Poltronics controllers what we have been used. There are multi-inverter like H type cascaded multi-level inverters are also there, which is most commonly now we are being used for the like 37 layers or the multi-layer H6 level, 7 level stage of multi-level inverters are there. Okay, so we are increasing the layers so that the total harmonic distortion can be reduced. Okay, that part can be improved with the help of multi-level inverters also. Okay, so these are the some of the Poltronics applications where we are using as a advancements in the photovoltaics. Okay, so thank you so much. So if you have any doubts regarding this, it's open to all.
So thank you, Dr. Sujit Kumar. Really a very nice presentation. Okay, in your second session, you have explained that how we can use the inverter, the single stage inverter, the multiple stage inverter, uh, and also the high frequency transformer. So now the discussion is open. If anybody would want to ask question to Dr. Sujit Kumar, then he can ask the question. Otherwise, I will ask question. So today also I have shared a YouTube video with you. So I just again shared you that I want certain comments from your side that what improvements can be there to make such type of skill based video for the stakeholders, either student or faculty or what improvements you desire, so that in the next project, because very soon we are going to have install another 40 kilowatt solar photovoltaic plant in our university, in our college. So I will definitely make a video on it. And if you have any suggestion that this should be included in it, then definitely we will cover that also. So yesterday I have shared you the two videos, one in English and one in Hindi. So if you have any comments regarding this, then please do share with me. So if anybody want to ask question to Dr. Sujit Kumar, he is welcome. He or she is welcome. So Sujit Kumar, question from my side. Just elaborate to a layman in a layman way that why we are going for high frequency transformer. Dr. Sujit, getting my question? Yes, Dr. Sujit.
Sir, voice is. Can you repeat it? Come again, sir.
Sir, my just question, just answer me in a layman way that what is the use of high frequency transformer in this all this process of converting from DC to AC and then again into DC and then using all this high frequency transform. What is the role of high frequency transform? Why we are not directly connecting to the our low frequency transform?
Sir, basically the inverter convert the DC voltage to the AC voltage. So there are different topology to achieve this. One with the low frequency inverters and one with the high frequency inverters. So since in the low frequency inverter, the input DC voltage is converted to the AC voltage using some MOSFET switching devices, which works at the frequency of 50 to 60 hertz. Then whatever this low voltage AC is step up by the power transformers, this makes the inverter circuit less complex but heavy and costly. Okay.
Okay.
But whereas in the high frequency inverters, the input DC voltage is boosted to the high DC voltage using the high frequency DC converter with the help of which uses the uh, I can say that high frequency pulse transformers, which is smaller in size. Okay. So then this high DC voltage is converted to the desired AC voltage using the same thyristor devices switching frequencies. So overall, the it makes the inverter circuit complex but lightweight and cheaper than the low frequency inverter.
So thank you very much. Okay, Dr. Sujit Kumar. Okay, and if time permits to you, then definitely I will invite you that you come to our college and share some practical experience with our participant. So really a nice talk. We will meet at again some more platform.